Okay, hi, linear algebra. So what I want to show you in this screencast is how to find an inverse of an n by n matrix and a strategy that is generalizable for all dimensions n, not just 2 by 2, okay? And when I show you this method, the first thing I'm going to do here is actually show you how to do it. And then we're going to ask the penultimate question, which always begins with why. In fact, all penultimate questions begin with why, okay? All right, but that's just my feeling about things. So here's what we're going to do. Here is a 3 by 3. Here is matrix A, and the question is find the inverse of A. And what I'm saying here is we would love to avoid the algebraic hassle of solving via systems. And what I mean by that is, if we were going to find the inverse of A, one method here is to go ahead and do this and set it up in this way and tell myself that I want to find the matrix the matrix inverse of A, and I'll call the inverse of A this one right here, A, B, C, D, E, F, okay, G, H, I. I want to figure out what 3 by 3 to multiply by that will yield what we know a matrix times its inverse always yields, which is the identity matrix, okay? And the algebraic hassle here is creating a system, right? So multiplying this 3 by 3 out down here, creating this 3 by 3, that's the result of these two, and then setting each portion equal to the terms over here. It's not saying that we can't get there eventually, but I think you can foresee it's a huge algebraic mess, and it's a nightmare. So I'm going to show you this new way. And this new way, hopefully it'll make you say, what in the world? And hopefully it'll beg the big question, which is why on earth does this work? Okay, here's what you're going to do. Set up. Here's what we set up. We set up an augmented matrix, but look at this one. This is a slightly different one. We set up an augmented matrix where we have the left-hand side is the matrix A, and look what's on the right-hand side. The right-hand side is I, okay? So we set up the matrix that we want to find the inverse of. On the right-hand side, we set up the I. And then here's what we do. Our goal is we're going to use row ops. So here we're using row ops in a slightly different context. We're going to use row ops to turn the A side here into I. In other words, I want to use row operations. And again, a row is this entire row here. It includes the left and the right. I'm going to use row operations to create 1, 1, 1, and zeros everywhere else if possible. Okay, and so now you see me working through the row ops. As a matter of fact, what you can do is if you want to practice, go ahead and do it on your own. Do the row operations on your own, try to get the reduced identity matrix here on the left-hand side, or you can just follow along with me here. What I did first was negative row 1 plus R3 equals R3. And then I multiplied row 1 by a half, got a new row 1. Making sure when you use the row ops, make sure you use the right-hand side of the rows here. Okay, so you can see even in these first two operations, look what happened. I has changed. And I'm going to keep going. Negative 3R1 plus R2 gives me a new row 2. We're here, all right? Then I do even some more. Again, this is all elementary, but do you see how what's happening is A is slowly but surely evolving to a place where I get, look at that. All right, my final picture. I have used row ops and I've gotten I on the left-hand side. And when you use row ops in this method, when you started out with, because we started out with A being over here, right? And it was I over here. When you've accomplished this, guess what is here on the right-hand side? This is the inverse of matrix A. Isn't that wild? Just completely wild. You have just found the inverse of A. Okay? Now, the big question is, why does this work? Why, or I guess how does this work? All right, and that's part of homework tonight. I want you to think about why in the world this works, and we'll answer that question tomorrow in class, because I do want to hear about what you have to think about this one. All right, let's make a couple of statements about this method. So when you're trying to find the inverse of an n by n matrix, so if we're going to generalize it, okay? So the goal here is to find a generalizable method. So given a square matrix A, to find the inverse of A, we do this. We set up the following augmented matrix. A, and then I is over here, right? And of course, this is only for a square matrix. And then we want to use row ops okay, if we can obtain through row operations the following, I on the left-hand side, then what's important to know is that what we have on the right-hand side, if I can get to a place where I can take this setup and get I on the left, what's here is the inverse of A. If we can obtain this throughout row ops, the inverse of A will always emerge here. All right, but now I have a question for you. Let's talk about a couple things here. Maybe we have a situation where, okay, let's say we have the following. Let's say we have a situation where this is the case. Okay, so let's say you have this matrix A right here, and I'm asking you to find the inverse of A. And here's the setup right here. Okay, and you can go ahead on your own if you'd like to. Here's matrix A, here's I, and you want to use row ops to get I on the left, and what will remain on the right is the inverse of A. And you can follow along with me, or you can try on your own, but I'm going to do a row swap of R1 and R2, because I see the 1 right here. When I do that, I did a row swap of R1 and R2, and then I'm going to add 5 times row 1 plus row 2, and I look at my cursor, right, to give me a new row 2, and then negative 6R1 plus R3 to give me a new row 3, and then I'm here. And maybe you see something happening here that's a little bit wild and wacky, but maybe you don't, see it, and so you'll just keep on proceeding. All right, I'm looking at this matrix here, and I'm just going to add, let's see, maybe you can divide everything by negative 10. Like if you're someone who just kind of plugs along, you'll divide this row 2 by negative 10 first, and then you try and get a 0 down here and a 0 above, right? Okay. However you get there, I'm just going to do this for a minute. I'm going to add row 2 and row 3, giving me a new row 3. And I'm going to write this out. And something odd should happen. Okay. This happens. Okay. So in the course of me trying to turn A into I, look what I hit. You hit a row of zeros. You hit a row of zeros. Once you hit a row of zeros, I want to explain this. Once in your course of trying to find the inverse of A, in your efforts to make this I, once you hit a row of zeros, the game is over. There is no way, once you hit a row of zeros, there is no way you're going to be able to accomplish 1, 1, 1. In these positions. There is no way you're going to be able to create I here, okay? The same is true if I was moving along, doing my work, and I all of a sudden hit a column of zeros. Once you hit a column or a row of zeros in A, or in what was A, en route to trying to turn A into I, if you hit a row or column of zeros, that means it'll be impossible to make this left-hand side I, or it'll be impossible to make this left-hand side look like the left-hand side of a reduced row echelon form. Let's write that down, okay? In the course, okay, en route to transforming A into I, if you ever encounter a row or a column of zeros, this means that your goal of generating I is impossible, okay, or is not feasible. What that means is A is what's called not invertible, or A does not have does not have an inverse. The n inverse of A does not exist. Okay, we'll talk a whole lot more about what it means for a matrix's inverse to not exist. One of the things you saw in a 2x2 world is that if the determinant of a 2x2 equals 0, that means that 2x2 is not invertible. The same thing is true here. I'll show you how it is that en route to transforming A into I, if you ever encounter a row or column of zeros, what that means is the determinant, okay, the determinant of matrix A equals 0, right? So this means this. The determinant of A equals 0. And we know if the determinant of A equals 0, this means that the inverse does not exist. Tomorrow, I'll talk about two things. How do you find the determinant of a 3x3? You maybe remember from our work with multivariable calculus last term, but I'll talk about two things. How do you find a determinant of a matrix that's 3x3? And also, I want you to think about why on earth this method even works. Like, why does this method work? It just seems so shady. All right, I'll see you tomorrow, everyone. Goodbye.